Let's take a closer look at the operation of the shift instruction. There are two types of shifts, logical shift and arithmetic shift. Each of these types have a separate instruction for right shift and a left shift. SHR and SHL are the right shift and left shift versions of the instructions for a logical shift. SAR and SAL are the right shift and the left shift instructions for the arithmetic shift. Typically the shift instruction is used in programs where you want to multiply or divide by 2 or powers of 2. Multiplication by 2 requires that the operand be shifted left by 1, and an integer division by 2 requires that the operand be shifted right by 1. Here is an example for shift left instruction for both the logical and the arithmetic left shift. Here I have an input which is a 32-bit value, and in hexadecimal that's dead beef. Here is the binary representation of the operand. Let's assume that the carry flag is a 0 to begin with. When I do a shift left of this operand by a count of 1, the most significant bit in the operand, which is bit 31 and has a value of 1, that gets shifted into the carry flag. So you see at the completion of the shift instruction, the carry flag has a value of 1. The rest of the bits are shifted left one place, so bit 31 will get the value of bit 30, bit 30 gets the value of bit 29, and so on. So that will leave a vacant position at the least significant bit, which is bit 0, and a 0 gets shifted into that bit. So if you continue the shift, you will see that the carry flag remains unaffected because the most significant bit here is a 1. So after the shift is done, the carry flag will still be a 1, and all the bits then continue to get left shifted. That leaves a vacant position again in bit 0, and a new 0 is shifted into the vacant bit. So that's how the SHL and the SAL instructions operate. The second example is for the logical right shift. So again, in this case, the input is dead beef, and this is the binary representation of this 32-bit value, and the carry flag is assumed to be 0 to begin with. Once we do a right shift on this operand with a count of 1, the least significant bit gets shifted out into the carry flag. So at the completion of the shift, you see that the carry flag has a value of 1. The rest of the bits all get shifted one place to the right. That leaves a vacant position in the most significant bit, and a 0 gets shifted into the vacant bit. The arithmetic right shift, SAR, is very similar to the logical right shift, except that in the vacant bit, instead of a 0 being shifted unconditionally, it is the most significant bit of the original operand that gets replicated. So that's essentially the sign bit which gets preserved as a result of doing the shift. So in this example here, since the most significant bit was a 1 to begin with, after the right shift is done, when we have a vacant position in the most significant bit, it is the original MSB, original bit 31, that gets replicated in the vacant position, as opposed to shifting a 0 unconditionally, which is what the logical shift right does. When we look at the status flags from the examples above, it should be clear that the carry flag is always affected, right? Because of it does not depend on what kind of shift we are doing. The carry flag always gets either the most significant bit or the least significant bit, depending on whether we are doing a left shift or a right shift. The sign flag, 0 flag, and parity flag are set according to the result of the operation. The auxiliary carry flag is undefined for a non-zero shift count. The overflow flag is only affected for a 1-bit shift count. So when the shift count is a 1, that's when you see the overflow flag updated, and the value that the overflow flag gets depends upon the shift. So if it is a left shift, the overflow flag is set if the carry flag and the MSB of the result are unequal. So what this essentially means is you're looking at the top 2 bits of the original operand. If the top 2 bits of the original operand are the same after a left shift, the carry flag and the MSB of the result are going to be the same, so the overflow flag will have a value of 0. If the top 2 bits of the original operand are different to begin with, after the shift, the carry flag and the MSB of the result would be unequal, so the overflow flag will be set. For a logical right shift, the overflow flag is always set to the value of the MSB of the operand, and for an arithmetic right shift, the overflow flag is always a 0. In the next video, we will see some examples which use these instructions, and that should give us a better feel for the shift instructions in action. Thank you.